So this video is all about using the context that we find in word problems and writing equations that describe the processes that are actually happening in those problems. And there are two things that we want to talk about first before we get into the actual skills being taught. The first is that our focus, as I mentioned, is that we're not going to just figure out how can we calculate our way from start to finish. That's a process we're very used to seeing throughout most of elementary school and even in the early years of middle school. You've probably done a lot of here's the word problem, let's calculate our way out of it. And that is totally fine in a lot of circumstances. But as we get into more complicated equations going on as you get into higher level math in school, or you get to the point where you're going to use math in the real world, we're going to get to some things that you can't simply calculate your way out of, either because the relationships are too difficult or because we have lots of things that we want to represent all at the same time. So our goal here is not just to write down what are the calculations that we need to find the answer to the problem, but how can we use equations and variables and numbers and the operations that we know to create an equation that actually represents the processes that are happening in the problem. And that potentially takes a relatively significant mentality shift away from solving a problem to modeling or describing a problem. But it is an important process because anytime that math is used in the real world to talk about how things happen, to model population growth, to model how money changes, it's all about not just what do we do to calculate it, it's about how can we describe the processes that are actually happening. And the second thing is we're not going to start with complicated equations like that. We're going to start with word problems that you probably can just see the immediate calculation for, ones where there are either only one or two steps to actually solve them, so we can get used to seeing and representing these types of equations without having to worry about the large complicated contexts. These should be things that you are either familiar with from life or you've seen in your years in school so far in elementary and perhaps the first few years of middle school too. So let's take a look at one of those types of problems that we could talk about. Talking about the last parts of a flight for a hot air balloon. After several minutes, it's dropped to 200 feet. It is dropped 200 feet to an altitude of 1,200 feet. And so the question that we can ask is, what was the hot air balloon's altitude before dropping? Now, you're probably looking at this equation and thinking, I immediately know what calculation I need to do. If it's down at 1,200 feet now, and we need to bump up to its original altitude, well, we can just add those 200 feet that were dropped back on, and we end up at our original altitude of 1,400 feet. And if that's the process that you're thinking in your head, that is exactly the process we would use if our only goal were to just calculate the answer to the problem. But that's not our goal here. Our goal is to use an equation to describe what is actually happening in this problem. And so one of the things that we need to do anytime that we're going to write an equation to represent a word problem is we need to identify what exactly our unknown is. Because if we don't know what our variable is going to represent, we can't write a very good equation. So in this case, the unknown variable, the thing we're trying to find, is the hot air balloon's altitude before dropping down to 1,200 feet. And so we can write that down as a part of our process. In fact, in class, I'm going to ask you to write those down so we can keep very strict progress on how we're going. Is just to identify the variable, the altitude of the balloon before it began descending. The second part of the problem, and the second thing that we need to do when we're writing an equation from a word problem, is try to think about it in terms of words. This is something that we call a verbal model for the equation. We're going to think to ourselves, what's actually happening here as the hot air balloon is starting at a certain altitude, dropping down by 200 feet, and then eventually ending up at an altitude of 1,200 feet. And so if we were going to draw this in terms of a picture, we would have a very shoddily drawn hot air balloon here that starts out at some unknown altitude. It cruises for a while. It drops by 200 feet. And then it continues onward at an altitude of 1,200 feet. And so if we're thinking about this in terms of what actually happens to the balloon from start to finish, well, there is a starting altitude, there is a change, and then there is a final altitude. And so this process here, the idea that we can start somewhere, make a change, and then end up at our final location, this is the process that actually happens. The balloon starts at one altitude, drops by 200 feet, and ends up at 1,200 feet. So we can describe that as the original altitude, that's the start, minus the distance it dropped, that's the change, we'll end up at our current altitude, will be the final. That process, although slightly more complicated to think about mathematically than is just the simple let's add 200 feet to the problem there, is one that actually describes what's happening in the problem. And this is going to give us an equation, not just that calculates it for us, but is going to tell us how we can calculate backwards for it and going to describe this scenario specifically. So now we can substitute the variables and the numbers that we know. Remember, this was start minus change equals final. Our variable was our original altitude. Our change was to drop, so it's minus 200 feet. And where we ended was 1,200 feet. So the equation x minus 200 equals 1,200, that describes the problem. And now when we solve this equation by adding 200 to both sides, as we've seen in earlier lessons, there is the familiar 1,200 plus 200 that we know we needed to do anyway. And now we can see that it's mathematically sound because it actually comes from the equation that describes that scenario. And so of these three processes, identify the variable, describe what's happening in words, and substitute the variable and the numbers that you know. By far, the process that takes the most practice and the one that we're really going to focus on is that second step, where we describe what is happening in words. We call these mathematical models because they talk about the actual process of what's happening in the problem rather than just a simple series of calculations to solve it. And so in the example problems that we're going to see here so that you can practice these skills, if you're having a hard time just working on the description, you can go ahead and do the quick calculation and see what you need, but try to come up with a simple idea for what is going on in the problem, such as start minus change equals finish, and use that as your verbal model. This is going to take a little bit of practice. We'll have lots of practice for you to do in class. But that is really what we're focusing on. So here are the first two problems that I'm going to ask you to pause the video, see what you can do about them, and then come back and see the answers before we go on to two more problems. So here are your two problems. We'll label them 1 and 2. Go ahead, pause the video, do what you can, and come back when you are ready to see the answers. Okay, so in this first problem, the unknown that we're looking at is how many jugs were lost during the trip. If we're thinking about a verbal model for this, where this is another one where we have an original or a starting number of jugs, something changed, and we ended up with a final number of jugs. So in this case, it is again start minus change equals final. We started with 200 jugs, we lost some unknown number, and we ended up at 165. We're not going to solve the problem yet necessarily, but in terms of just looking at what is the context for that problem, this is what we can do to write a verbal model and an equation that describes the process. We started with some, we lost some, we ended with some. So start minus change equals final. In the second problem here, we can think about it in terms of drawing a picture. We have a stalagmite in a certain cave underwater in a pool 55 feet deep. That means from the base of the stalagmite to the water is 55 feet. If we know that the distance between the tip of the stalagmite and the top of the water is 41 feet, we can talk about how tall the stalagmite is. So first question, the unknown is how tall is the stalagmite? And this is not a question of start, change, final. This is a question of there is a total depth of that water, and we can represent that total depth as a combination of the stalagmite's height and the distance between the stalagmite and the water. And then we can calculate that out to be 14 feet. And so when we're actually writing this equation, we're going to say the depth of the pool, this is a total, being made up of a bunch of components, the height of the stalagmite plus the distance to the surface of the water. And then we can find out that the stalagmite itself, after we write the equation, x plus 41 equals 55, height plus distance equals total depth, to be 14 feet tall. Two more problems for you to work on before the end of the video. Go ahead, pause the video, see what you can do about writing both the verbal model and the equation that represents these word problems. Pause the video, come back when you are ready to see the answers, and end this video lesson. So this first one on the top is another example of a total being made up of certain parts. And in this case, the total is made up of, there's the anchor and the lake that goes down to the bottom, and there is some extra rope that is left over that's being held in the boat. Because Gunther here is tying 300 feet of rope to an anchor and dropping the anchor into the water. That means the total length of the rope is a combination of the extra and the amount that it takes to get to the bottom of the lake. So the depth of the lake, which is the unknown, plus the extra rope that we have, which is 55 feet, is going to be equal to the total length of rope, which is 300 feet. Here again, we have a total, we have an overall value, and we're using smaller numbers to create that value, because that's how totals are actually created, not by a series of subtractions, but by saying the length of the rope is going to be however deep the lake is plus the extra. And so that's the problem that we would write here. The depth of the lake plus the remaining rope is equal to the total length of rope, and find out that the lake is 245 feet deep. In the last problem, Ingrid is painting several rooms in her house. Each room requires the same amount of paint to complete. If 5 rooms require 15 gallons of paint, how much paint is needed for 1 room? Now, this is slightly different than the ones we've seen before. Here we have a total amount of paint still, but now it's not a question of adding things up. It's a question of taking multiple copies of rooms. So we have a certain number of rooms, and each of those rooms are going to require a number of gallons of paint per room. So we can calculate if every room, for example, required 20 gallons of paint, which it doesn't in this case, we could say 20 gallons for 2 rooms is 40 gallons, because 20 times 2 is 40. 20 gallons for 3 rooms is 60 gallons, because 20 times 3 is 60. 20 gallons per room times 10 rooms is 200 gallons, because 20 times 10 is 200. And so that's how the total amount of paint is going to be equal to the number of rooms we have times the number of gallons that it takes to paint each room if they all take the same amount. Here we know our total is 15 gallons of paint. We know our number of rooms is 5. And our unknown is the paint needed for 1 room. So here we have an equation: 15 equals 5x. Number of rooms times the paint needed per room is equal to the total paint needed. Again, building a total from smaller pieces to find out that we need 3 gallons per room. Again, the 3 things that we're going to think about when we're writing an equation that models a context given in a word problem are: what is the variable? What's the unknown? How can we describe it in words so we have a better idea how it is that we're going to put the numbers together, and then substituting the variable and the numbers that you know. Again, the hardest part of this process is going to be the description of the equation, writing a verbal model for that equation, describing not just the calculations you need to get to the answer, but actually what is happening in the problem.